Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the online data structure class. What we will be doing today is to start the first online lecture on chapter 5, which is hashing. I will be discussing the basic concepts of hashing. What type of problem do we encounter when we use hashing, and what type of solutions are available to us. The type of operational advantages and disadvantages hashing has on other abstract data types that we have learned so far, such as arrays, linked lists, binary trees, and also discuss in which applications hashing is applied the most. इस लेक्चर में हम हैशिंग के बेसिक कॉन्सेप्ट्स डिस्कस करेंगे। हैशिंग में हम किस किस्म के प्रॉब्लम्स इनकाउंटर करते हैं जब हैशिंग की जाती है और उनके क्या सॉल्यूशंस अवेलेबल हैं। हैशिंग की क्या एडवांटेजेस और डिसएडवांटेजेस हैं दूसरे डेटा स्ट्रक्चर्स पर जो हमने आज तक पढ़े हैं। फॉर एग्ज़ाम्पल अरेज हैं, लिंक लिस्ट्स हैं और बाइनरी ट्रीज़। हैशिंग की जो एडवांटेज है दूसरे एब्स्ट्रैक्ट डेटा टाइप्स पर, उनकी सबसे ज़्यादा एप्लीकेशन क्या है। लेट्स मोटिवेट ourselves. Let us assume that we want to search for a particular item in a database of 20 million data items. Question is, how long would it take to find for a successful search? In other words, what would be the time complexity order in this case? And the second question is, how long would it take for an unsuccessful search? What would be the order of complexity in this case? Well, the answer lies it all depends on the data structure that we have selected to execute the search. मोटिवेशन के लिए हम एक प्रॉब्लम ले लेते हैं जिसमें हमारे पास 20 मिलियन डेटा आइटम्स हैं और हम एक डेटा आइटम उसमें ढूंढना चाहते हैं। सवाल ये कि सक्सेसफुल सर्च का टाइम कॉम्प्लेक्सिटी ऑर्डर क्या होगा, और दूसरा सवाल ये है कि भाई अनसक्सेसफुल सर्च उसका टाइम ऑर्डर कॉम्प्लेक्सिटी क्या होगा। बेसिकली इनका जवाब जो है डिपेंड करता है कि हम कौन से एब्स्ट्रैक्ट डेटा टाइप से सॉल्यूशन इम्प्लीमेंट करेंगे। इन द क्लास वी हैव लर्नड सो फार arrays, linked lists, and binary trees abstract data types. For linked list, sorted or unsorted, the search time will be order n. Linked list needs to iterate for search operation from the beginning, which is the head node, and going all the way to the tail node. Basically, it has to scan all the number of entries in its domain for the worst case scenario. For binary tree search, the search time will be order log n. Binary search tree algorithm begins its search at the root node and trace the path downward onto whether to go to the left or right subtree, comparing values accordingly such that it can drop the left or right subtree. Log of 20 million is approximately 24. Now 24 represents the number of iterations we need to do on average to find the node we want out of the 20 million nodes, taking into account that this is a balanced tree. Can we do even better than order log n? Yes, we can. We can lower the number of search iterations further by using hash table abstract data type, which gives us a constant order 1. क्लास में हमने अब तक अरेज, लिंक लिस्ट्स और बाइनरी ट्रीज पढ़े हैं। लिंक लिस्ट सॉर्टेड हों या अनसॉर्टेड हों, सर्च टाइम जो है वो ऑर्डर n रहेगा, क्योंकि सर्च हेड नोड से शुरू करेंगे, ढूंढना और टेल नोड तक जाएंगे वर्स्ट केस सिनेरियो में। एक बैलेंस्ड बाइनरी सर्च ट्री का टाइम कॉम्प्लेक्सिटी ऑर्डर log n है। जब सर्च आप शुरू करेंगे तो वो रूट नोड से शुरू होगी और लीफ नोड तक इटरेट करेगी वर्स्ट केस सिनेरियो में। log ऑफ 20 मिलियन अप्रॉक्सीमेटली 24 है, और 24 जो है वो रिप्रेजेंट करता है नंबर ऑफ इटरेशंस ऑन एवरेज नोड फाइंड करने के लिए आउट ऑफ 20 मिलियन नोड्स में। 24 जो है आप इस तरह इसको समझ लें कि आपका जो BST है उसके 24 लेवल्स हैं, और रूट नोड से शुरू करके हर लेवल पे जब नीचे जाएंगे आप ये डिसीजन करेंगे कि आपने लेफ़्ट सब ट्री पे जाना है या राइट सब ट्री पे। सो इस तरह आपने 24 डिसीजंस करने हैं एक 24 लेवल ट्री पे। क्या हम इससे बेहतर कर सकते हैं? बिल्कुल, अगर हम हैश टेबल एब्स्ट्रैक्ट डेटा टाइप यूज़ करें और उसका कॉम्प्लेक्सिटी ऑर्डर जो है। Our outline for chapter 5 will consist of the following topics. First is the general idea, basically how to design a hash table, what type of hash function we will be requiring such that search operations can be performed in constant average time. There are different types of hash functions that we will look into: separate chaining, open addressing, rehashing, and extendable hashing are problem-solving techniques that we will discuss later in the slides that can be used to design our hash table. In our goals, we will see several methods of implementing the hash table, compare these methods analytically, show numerous applications of hashing, compare hash tables with binary search trees. We have 3 terminology points here. The first point is that hash table abstract data type is a data structure that supports only a subset of the operations allowed by the binary search trees. The second point is implementation of a hash table is called hashing. And the third point states that hashing is a technique used for performing insertions, deletions, and find in a constant time. The first point implies that although hashing is a technique used for performing insertions, deletions, and finds in a constant time order 1, but operations that require finding minimum value or finding maximum value or even printing the entire data in sorted fashion, hash table is not efficient, and the reason being data in hash table is stored in random fashion, whereas in binary search tree the data is stored in ordered fashion. That's the reason why ordering operations are not supported in hash. Let's develop general idea about hashing. The general idea behind hashing is to directly map each data item into an address in memory using some function. The hash function here takes a key as input and, and returns a value that is the index of an array where the key value will be mapped. In components of hashing, a hash table is an array of some fixed sized m. A hash function maps a search key k to some location in the range between 0 and m minus 1. The purpose here is to design a kind of a table that can perform insert, delete, and search in constant average time, and this implementation of the hash table is called hashing. The hash function is not defined in this slide, but let's assume that the hash function takes string data type as input instead of a number. Last name Javed as key is input into the hash function, and let's assume the hash value computed is index 1 of the hash table. One of the desired properties of the hash function is to be simple, such that it computes the hash values fast. The more complex the hash function is, more computation time it will be required to compute the hash value. You do not want to write a very complex hash function where simple binary search defeat the purpose of hashing. The second desired property of the hash function is the distribution of keys uniformly over the indices of the hash table. One of the problems to deal with in choosing a hash function is what to do when two distinct keys hash to the same hash value. If k1 and k2 are two distinct keys, then h of k1 equaling h of k2, we have a problem which is called collision. Here in this example, where our hash function takes string type as input key, the string keys here are last names Javed and Hamid. Both key values are resolving to the same hash value of 1, which implies that a collision has occurred. Two important topics in hashing are how to select a hash function and second, how to resolve collisions.